Hello and welcome to Lesson 7 of this Introduction to Probability of Wolfram. The topic for this lesson is random variables. Let's begin. So far, we've addressed probabilities as simple constants, but more often than not, functions vary based on some other value. If we think of the cat and mouse example last lesson, as the number of cats increases, we would expect the mouse's probability of survival to decrease. A random variable is a function defined over the sample space of an event. You'll learn the essential characteristics of random variables and their related functions: probability distribution, probability, PDF, and CDF. You'll see how to use those functions to make any random variable. Often, for a given experiment, the goal is to represent a function of the result. For example, if you roll 2 dice, the goal isn't the sequence 3, 5, but the sum 8. In a best out of 5, the goal is not the sequence win, lose, lose, win, lose, but the loss overall. Formally, a random variable is a function defined over the sample space of an event. So why use random variables? It's to summarize event sequences through functions of interest. At first, when I learned this, I was very confused. If a random variable is literally defined as a function, why call it a variable? Let's take an example. A standard variable only contains a single value, like 2, but a random variable is random. It can take any number of values based on a probability function. The random real function takes any value from 0 to 1. If we run it, the random variable will have a random value. So a random variable is a symbol representing some random values. But why would you want to do that? Think of all the experiments we talked about so far. Indeed, the second goal is to encapsulate many random experiments in a single symbol. Okay, I'll admit it, it's a bit confusing at first. A random variable can refer both to a function and a variable, but it's usually meant for the variable part. That means the representation of the probability function. When you want to refer to the actual math function specifically, that's called the probability density function, or PDF for short. It's a real-valued function that satisfies the axioms of probability. Most importantly, that it's non-negative, and that the sum of all values, or area under the curve, is 1. These two things, derived from the axioms of probability, determine whether a PDF is valid or not. Okay, let's try to create a PDF. First, choose the shape of the function. I like the roundness of the sine function, so I'll go with that. And now you see it. Second, make sure your function is non-negative. An easy way to do that is just to subtract the minimum value. That way, nothing can be below 0. Finally, normalize your function so that the sum is 1. I'll just divide the function by the integration of the function on the entire domain. Don't worry too much about this step for now, I'll explain it further in the next 2 lessons. But simply put, for a discrete function you want your complete sum to be 1, and for the continuous function you want the complete integration to be 1. The probability distribution function allows you to construct any random variable. Just write the PDF and the domain. For example, the previous function can become a distribution with domain 0 to 2 pi. Most functions seen in this section take a probability distribution as input, so it's quite useful to have in hand. Okay, let's say you have a distribution. Then use PDF to get the PDF out of the distribution. And now we can just plot the distribution. We can intuitively see that most of the probabilities, that is the area under the curve, are between 0 and 3. But how can we confirm it? For that, you need the cumulative version of the PDF. The cumulative distribution function, or CDF for short. All it does is just add up the probabilities of the PDF. The PDF answers the question if the variable is equal to some value, whereas the CDF answers the question if the variable is less than or equal to some value. The axioms imply the CDF monotonically increase from 0 to 1, and it can be seen as the function of the area under the curve of the PDF. Plotting it, you can indeed see that most of the probability is between 0 and 3. Now that we have random variables, it'd be nice to actually get back to what we actually wanted: probability. That's easy. Use the probability function to give any probability over the distribution based on the predicate. Oh, and this symbol means distributed, by the way. So, for example, what's the probability our variable is greater than pi? Just use the condition greater than pi, and you get this. Greater is the opposite of less than or equal to. So you could use the complement of the CDF to get the answer in this case. Oh, and you want the conditional probability? No problem. Add a condition with a condition symbol. For example, if x is greater than pi divided by 2, what's the probability that it's between pi and 3 pi divided by 2? And you get your answer. If you need to compute faster and want the numerical probability, just use n probability. Okay, let's do an example. You're given the heights of singers in a dataset. What is the probability that a randomly selected singer is more than 68 inches tall? First, load and aggregate the data. Then make the function to express the data. Okay, then visualize the data, always useful. Then calculate the probability, and that's about 38%. Great. In the beginning of the lesson, I mentioned that we were rarely interested in the sequence of dice rolls, and more so in their sum. So continuing on that thought, what's the probability of getting a sum higher than 7? Think about the dice rolls sequences and get their sum. Now aggregate the result. Then make it into a function. Visualize. And get our answer. That's the probability of x greater than 7 on our distribution function. And this gives us 5 divided by 12. Okay, fair. The code in the last two examples is a bit ugly and rough, with these weird data functions. These functions represent non-parametric distributions, which will be seen much later in lesson 20. Wolfram functions for that will make the process much easier. But for now, focus on the process. Load, aggregate, visualize, calculate. You should also remember, a random variable is a function defined over the sample space of an event, representing an event. In the Wolfram language, use probability distribution, probability, PDF, and CDF for random variables. The two next lessons are dedicated to the two fundamental types of random variables.